So, guten Abend, sehr geehrter Herr Präsident, liebe Kolleginnen, liebe Kollegen, liebe Gäste. Ist mir eine Freude, Ihnen heute unseren neuen Kollegen Jonathan Home vorstellen zu dürfen. Jonathan stammt aus Newcastle upon Tyne und verbrachte dort auch seine Jugend- und Schulzeit. Mit 16 konzentrierten sich seine Interessen auf Mathematik, Physik und Chemie und auch Violine, wobei die Mathematik zu abstrakt war, die Physik, da erfuhr man nicht die Wahrheit, und die Chemie, die konzentrierte sich auf das Auswendiglernen von Formeln. Mit 18 wurde Jonathan dann auf die Feynman-Bücher aufmerksam und entdeckte, dass die Physik an der Universität rigoroser daherkommt. Die Kombination von Physik und Mathematik erschien ihm eine interessante und geeignete Wahl für das Studium. Studiert hat Jonathan in Oxford nach Test und Interview durch 2 Tutoren. Der erste macht ihm klar, dass er das Thema Wellen wohl noch nicht ganz verstanden hätte. Mit dem zweiten geriet er in ein Argument über Wirbelströme. Das schien allen gefallen zu haben, und Jonathan begann sein Studium, wobei er bald lernen durfte, dass das einfache Leben vorbei sei, was die Sache dann schließlich interessant gemacht hat. Im 3. Jahr erklärte ihm Vlasco Vedral die Experimente von Alain Aspect zur Verschränkung der Photonen, und im 4. Jahr waren Atom- und Laserphysik die Highlights, was die weitere Karriere in Richtung Quantenoptik vorspurte. Auch erwiesen sich die Übungen mit der Violine im Speisesaal des Colleges als besonders interessant. Die Pianistin, die dort auch zu üben pflegte, ist heute seine Frau. In seiner Doktorarbeit, das war 2002 bei Andrew Steen, kamen Jonathan Interesse in Mathematik, Quantenmechanik, Atom-Laseroptik voll zum Zuge. In seiner Arbeit hat er 2 Ionen in den Grundzustand gekühlt, um sie dann zu verschränken und das Resultat zu tomographieren. In einem anschließenden ersten Postdoc hat er diese Experimente weiter ausgebaut und ein erstes logisches Gate mit 2 verschiedenen Calciumisotopen implementiert. Dann ging es weiter mit einem Lindemann Fellowship über den Teich 2007, Boulder zu Dave Wineland. Dort hat er zur weiteren Entwicklung seiner Experimente den Transfer von Verschränkung oder Entanglement, Sie konnten das letzte Woche bei Matthias Christandl lernen, hat er also diese Verschränkung zwischen 2 Systemen verschoben, von einem elektronischen Freiheitsgrad auf einen mechanischen Freiheitsgrad. Das soll einmal helfen, Quanteninformation von stationären Qubits und beweglichen Qubits hin und her zu schieben. Jonathan blieb schließlich 3 Jahre in Boulder und baute in dieser Zeit einen vollprogrammierbaren 2-Qubit-Quantencomputer, mit dem sich jede Operation, jede unitäre Operation ausführen ließ. Seit seiner Ankunft an der ETH-Zurich im Sommer 2010 baut er sein Ionenfallenlaboratorium am Hönckerberg auf. Als Assistenzprofessor im Institut für Quantenoptik will er seine Experimente mit verschiedenen Ionen weiterentwickeln und den gezielten Einfluss von Reservoiren mit einbeziehen. Wie sich der große Feind des Quantenrechnens, die Dissipation oder Kohärenz, für die Manipulation und das Rechnen mit Ionen nutzen lässt, das wird uns Jonathan in seinem Vortrag erklären. Turning an enemy into a friend. Quantum Computation and Dissipation. Jonathan Home.
Okay, thanks very much, Gianni, for the nice introduction, which I understand a little bit, but I unfortunately do not speak German very well, so I shall continue in English. I apologize for that. So indeed, I'm going to talk, the topic of this lecture is turning an enemy into a friend, and it's really what I would like to talk about today as well as talking about quantum computation and decoherence, so the loss of coherence in quantum systems, is really an effort to match up two worlds and two ways of speaking about physics. And the basis for this really is that we have a big problem in physics, and that is that, well, on the left side, as you can see, we can describe microscopic interactions between atoms pretty well, and quantum mechanics does this for us. We have a great problem with quantum mechanics because when we put together too many atoms, the problems become so hard that we struggle to link small-scale systems and small-scale interactions to bulk properties, such as what you might see on the right-hand side here. And this is a lump of a ceramic which, at 70 Kelvin, is superconducting. That is, the result of that is that it expels magnetic fields, and so what you're seeing here is this lump is in a magnetic field and it's levitated because it's expelling all the magnetic field. Okay, and so one problem here in physics is that these high-temperature superconductors are complicated quantum systems, and they are quantum systems that we can measure in big lumps like this of 10 to the 23 or so atoms. And the problem we have is that we would like to, if we would like to understand these systems better, is find out what microscopic models are underlying the physics in this bulk system, but making this connection between the two is extremely hard. And the reason it's extremely hard is because complexity in quantum systems grows dramatically with the number of atoms that we put into the system. There's another problem in which we go from the microscopic to the macroscopic, though, and that's really in a connection between what we might say was the old physics of the previous century, classical mechanics, and between that and quantum mechanics. And what do we see there? Well, when we look at things like atoms, and this is really a picture of two atoms from our lab last year, when we look at atoms, we see that they behave very well as quantum mechanical objects. They behave according to the rules of quantum mechanics. But when we look at things like a cat, and this is the cat that I had in Boulder in my house, they don't behave particularly quantum mechanically. In fact, it's very much classical mechanics that has behaved. And really what these are is two different sets of rules that seem to describe the world well at different length scales or different complexity scales in a way. And so in exploring the move from the microscopic to the bulk properties, the other thing that we're doing, in a sense, is exploring how quantum mechanics and the complexity of the way in which quantum mechanics turns into classical mechanical systems. And I want to today give you an insight into basically all of these problems, how we're currently approaching these problems, and is there some solution to how we can deal with these problems. So what is this computation problem? Well, first, I should just tell you, or you could ask, is it important? Okay, and so let's see if it's important. Well, clearly the US Department of Energy thinks that quantum mechanics is somewhat important. And why do I say that? If you look at what the US Department of Energy's computers, their supercomputers, are doing, it's listed here as a number of different tasks, and you can see the percentage of the time that they spend doing these different tasks. And if you look where I've put these arrows, these are all areas where quantum mechanics is extremely important, okay? So a lot of the supercomputing power of the Department of Energy is going into doing basic quantum mechanics. And that's partly due to the complexity of trying to integrate up or deal with large-scale quantum systems. Okay, and if you go to a computer scientist and ask about quantum systems, then integrating Schrödinger's equation on a many-body quantum system is generally called hard. And when they say hard, what they mean is if the problem gets bigger, the amount of computation you have to do, the amount of resources you have to put in to do the computation scale exponentially, okay? And so one thing we're looking for is whether we can reduce this maybe from being not quite exponential to being something less than exponential so that we can build a computer that could maybe deal with these problems. And let me just exemplify the sort of, when we go to the lab and try and deal with quantum systems, what this exponential means, okay? So here is a plot of a matrix, essentially. And this matrix is telling me all or some of, in fact some, because I'm using the real part here, but a lot of the information about a quantum system, and it's a quantum system of two atoms with two internal states. And you can see there aren't so many elements of this matrix. In fact, there are 16 in total. Okay, and to gain the information about this sort of system, I need about 900 measurements. And the 9 is the number of measurements I actually need to recreate that matrix, but the 100 is all about getting enough statistics to really use this as or to produce something that's a statistically good matrix. But now let's look what happens when we go to 8 qubits, okay? And this is a result from the group in Innsbruck from 2005. Again, I have drawn the matrix that describes these 8 qubits, okay? But now you can't see any of these elements except for these vertical blue lines. And these are the remaining elements of the matrix. But in fact, there are a vast number of these elements all throughout this matrix, okay? And this is the matrix now describing just 8 qubits, and previously we're describing 2. So let me give you an idea of how complicated that makes things. So to actually find that matrix out, what you have to do is take 656,000 measurements, okay? And then you have to sit for a week with your computer while it churns through all the measurements and turns them into a matrix like that that tells you what your quantum state looks like, right? And this really is an illustration of this exponential thing that as you grow the system up, it gets very much bigger to deal with in terms of classical information, in terms of the information we process in our daily lives. So having illustrated what the problem is, I'll go to the overview of the talk. So first, I want to describe the sort of basic physics behind why it may be hard to do these sort of things. What is it that makes quantum computing or makes a quantum system exponentially hard to increase in size and keep on computing? I'll go on to talk about whether there's a solution, and indeed, by a slip of the tongue, I mentioned that in my previous sentence, right? What I'm going to tell you about is using quantum systems to do computation, and it turns out that that does offer an advantage, and in a sense, it's based in some of the reasons why classical computation cannot do quantum systems. And then finally, I'm going to talk about what we can learn from maybe building up towards building quantum computers or trying to build quantum computers. And in particular, I'll focus on how we learn about systems interacting with their environment and how that's actually a fairly complicated problem and may offer us interesting insights into quantum mechanics. So with that, I'm going to go back all the way to not even the last century, but the century before. And this is really the results that started people on the path to quantum mechanics. And what this is somebody's put through a spectrometer the emission from hydrogen atoms, okay? And so what you see is a series of discrete colors of light. And in fact, they correspond to different energies of light that are emitted from the hydrogen atom. So why does the hydrogen atom only emit at particular energies? Well, it's because the electron, a hydrogen atom is a proton and electron, and the electron likes to live in certain shapes around this hydrogen, the proton, okay? And it only takes discrete states. And these states are the shapes of its existence, if you like, around the proton. And so here I've drawn a bunch of these. And the thing about this is that if the electron is in a certain shape, or if it's in a different shape, it has a different energy, okay? And since there are a discrete set of states, we get discrete levels in energy. This is stuff that went on at the turn of the century. We've now developed such control in atomic physics that we can actually pick out and manipulate individual atoms, but not only that, we can take these individual atoms and we can manipulate the individual quantum states. So I could point at this one, and you could say to me, go to your lab and prepare this guy, and I could go and have a good shot at trying to prepare this guy, okay? You might have to give me some time, but I maybe could do it, okay? So these states are important, but there's more important parts to quantum mechanics than just these states or wave functions, okay? And so the real thing comes that when I can prepare systems in, if you like, what we call superpositions of two states. So let's just start by preparing one state. Remember, these states have different energies, and I could try and prepare it all in this particular energy level here. So I prepare this one state here. But the quantum mechanical, or the interesting quantum mechanical stuff, doesn't come when I just prepare one of these states. It comes when I prepare two, okay? And if I look at this, if I try and look at this atom, what will I find? Well, if I prepare it in an equal mix or an equal superposition of these two states, what I find is that when I measure an atom, I get either one result or the other with equal probability, okay? And so if somebody gives me 100 atoms all prepared the same way, 50% of the time I will find that I get energy 1, or this state, and 50% of the time I'll get energy 0. But there's much more to quantum mechanics than that. And the key thing in a quantum mechanical system is that these states don't just have probabilities to attach them, but they have a fixed relationship. And it's a little bit like a clock that ticks inside the atom, and it tells you the time of this guy relative to the time of this guy, okay? And so what do we want to do, or can we take advantage of that clock? This is a little bit extra. In a classical system, we really just have these probabilities, and this is the extra that gives us quantum mechanics. So if you have a clock, what do you want to do? You want to tell the time, okay? And so how do we try and tell the time in an atom? Well, we come along with another oscillator, and in this case, it's usually a laser beam, which has a very precisely defined frequency. And this also, if you sit in a point in space, this wave travels past you, and you feel an oscillation, and that gives you a time. It gives you another ticking clock. And what happens to this atom if we turn on a pulse of light is that dependent on the relative time of these two clocks, we can put the atom either up in that top state, from the 50% state, if you like, we transfer it into the top state, or if the clocks are out of phase, and I'm going to show you that in an experimental result. So here we pulsed on this light, we transferred it to the up state, and here at the top, the time is the same, that's the 0 time difference between the two, and we can see that the atom is now all in the energy state 1. So now we go such that the phases of these are opposite, okay? And instead of now transferring the state into this upper state, we transfer the whole atom into this lower state. And that's what's happening at the bottom of the curve. You can see these two clocks are pi out of phase. That's what this axis on the bottom of the graph is. And what that means is we're in state 0. And as we tune the relative phase of these two clocks, you can see there's a gradual transition between being in state 1 to being in state where we've got an equal superposition again, equal probability of being in state 1 and state 0 to being in state 0. Okay? And this gradual transition is really the signature of quantum mechanics, this sinusoidal oscillation. Okay, so that's a single atom. But in our labs these days, we don't just play with single atoms. We actually typically play with many atoms, okay? And in an ion trap experiment, this is not very many. It's, at the moment, 2, okay? So what happens with 2 atoms, okay? Let's prepare them in exactly the same state we started with before. And again, we're going to try and compare them with this laser oscillation, okay? So we introduce our laser and its clock. And now let's look at what we get for the 2 atoms, okay? And what we find, and you should watch out because these axes have just shifted along. They're now between minus pi and pi, and formerly it was between 0 and pi. But what we find is the same as we saw in the previous slide, if you like. We see this nice oscillation, and indeed we see this nice oscillation for both atoms, okay? And because they were prepared in the same state, we see that this peak is at exactly the same point for each atom, and that's because they were prepared with the same clock. They had the same time, okay? And we were referencing them to a common clock. So that's one way of looking at 2 atoms, okay? These atoms were completely independent. This one, if you like, had its own clock, and this one has its own clock. But there are other states we can make in quantum mechanics, and that is where instead of every atom having its own clock, the clocks can be shared, okay? And here we've got a system where, again, it's 50% chance. If you measure this guy, you'll find 50% chance in this state, 50% chance in that state. Again, if you measure this guy, you've got a 50% probability of finding it in this state and 50% in this state. But now let's look and let's try the same technique we tried before on this shared clock system. And what we see is if we isolate this one system, reference it to our laser, now, and I can't show you any data for this, I'm afraid, but this is a theoretical curve, the curve is completely flat at 50%. Okay? So something pretty dramatic has happened, and definitely we don't have access to this clock by looking at this one system. And then I'll do the same thing, but on the other atom, maybe the clock is hiding there. Well, what I see is that it's not. I get 50% again, and I can't get access to the information. So how can I get access to this shared clock? Well, I have to do something a bit cleverer, okay? And so instead of now looking each time whether I got 1 and 0, what about I measure both of these guys. I measure this one, and then I measure this one, and I compare. If I got 1 here, what did I get here? And instead of looking at the actual results, the actual 1 or 0 I just say to myself, am I correlated with what was found at the other end? Okay, so in one case I might get 1, and if I got 0, I'd find I'm not correlated, I'm anti-correlated. But in another case, I might get 1 for both, and then I've got correlations. And what happens if I do that? Well, back comes my fringe, and here I'm reading out the clock all over again, okay? And so these correlations are, if you like, special in the sense that these two particles could be the opposite side of the world, but they're still sharing this quantum mechanical phase. They're sharing this clock, and the only way I can find out about that clock is by bringing information from these two parts of the world and putting it together and looking at correlations between the two. And this is really something quite dramatic, actually, in quantum mechanics. And the reason it's dramatic is that if you look at classical systems, the correlations that are shown here are more than you can get in a classical system, okay? And so there's actually more information stored at these remote, or more mutual information at these remote locations than you could ever get in classical mechanics. And that's a real problem if you want to do quantum mechanics using classical mechanics. And let me see if I can illustrate that further down the line. Okay, so when I say classical mechanics, actually what I'm talking about in quantum mechanics is this non-locality, this shared information at distant locations, is actually more, it produces more correlations than you can get for any theory you make based on local variables. And what am I going to talk about local variables? Let's imagine that some guy came along and imagined I could make measurements on my two systems and tried to preempt me. So he fed some information saying, look at all the measurements you might make here. I'll store that information here, the right results, to try and make it really highly correlated with the right results for anybody measuring here, such that I get strong correlations. Well, it turns out people have thought of lots of weird and wonderful ways to do this, and they can never make it work out that for any measurements that are produced here, or certain sets of measurements, that the local theories, that these conspiracy theories can beat the quantum mechanics, okay? And so that really tells you that this quantum mechanical correlation is something outside the world of local physics, and in a sense, it's local information. This is non-local information now in quantum mechanical systems. Okay, so now let's think about a complicated quantum mechanical system, right? And as I say, I play with few trapped ions, so 5 for me gets complicated, okay? So here's 5, and I'm trying to represent each quantum system by this little circle. And let's imagine there's lots of these non-local correlations between all the system. And what I have to do, if I'm doing it on a classical computer, these are not natural to my system. These correlations are not at all natural. So I have to store extra bits of information for every one of these that exists. And that's actually something that's very hard to do, especially because it's not just between pairs of these things that I can get these non-local correlations. And I should just point out, I haven't said it before, we call this entanglement. It's not just pairs. We can also get situations where these clocks are shared between 3 particles. They could be shared between 4 particles. And really, you can only pull out the information, remember, about these clocks when I bring together observations of all of these 4 particles. And in fact, if I have n systems in my complex system, if you like, n individual quantum systems making up my quantum system, I can even have n particle entanglement in that sense that all of these things would have to come together. I'd have to use information from all of them to recover information about the quantum mechanics within the system. And that's a real problem for a classical computer because a classical computer doesn't have non-local correlations. It's everything in a classical computer, the information is defined at particular points in space. Okay, and that's a distinct difference, and that's something that caught the eye of Richard Feynman back in 1982. And really what he was asking, or part of what he's asking in this paper, it's actually a speech he makes in 1982, is how about a computer which could reproduce these correlations? Okay, and now I'm going to the language of Feynman, and you know, you sort of get a sense for how he talks through the way he writes, and he says things like, it had better be a quantum mechanical device, okay? And that's because really quantum mechanics is the only theory we know that has these, or it's the only theory that we know and have used to make predictions and seen them in physics that can reproduce the correlations we see in quantum physics. So the question then is, what could it do? Okay, is there something that this sort of computer could do that other computers can't do, and does that extend to quantum mechanics? And it took about 10 years for this to be resolved, but just the finding of one particular algorithm really opened this question up. And the algorithm might sound peculiar at first, okay? So what this algorithm does is, on a quantum device, this algorithm would be able to find the prime factors of a large number using what they call polynomial resources using this quantum mechanical computer, okay? And what I'm talking about in polynomial, previously I said exponential was something that computer scientists say you can't do, it's hard, okay? Polynomials may seem pretty bad to a lot of you. It probably will seem pretty bad to us as we go towards building a quantum computer, but crucially, computer scientists would tell you that this is a computable system if you can use polynomial resources that scale polynomially. Okay? And why is finding prime factors of a large number interesting? Well, it's actually interesting to all of you in this room because the cryptography on your email system relies on the fact that a normal computer cannot find the prime factors of large numbers. Okay? And so this is actually an important problem in cryptography. The really important result, though, is that this takes quantum devices beyond what a classical system can do. It defines a new set of problems in computation which a normal computer couldn't do, but now there's this new type of device working using quantum mechanical rules that could potentially do. And that's a sort of mindset change in how you think about computational physics. Oh, and the final point about that, I guess, the really interesting thing for physicists about these sort of problems that are hard classically, right, is that one of them is to simulate quantum mechanics. In fact, there's some stipulations about that, about being fairly local with your interactions, et cetera, but really this is the exciting point for a physicist in this field. Okay, so how do we realize a quantum computer? Well, actually, the sort of layout was realized or was drawn up for us earlier than this result from Peter Shor, and that was by David Deutsch in 1985. And what he did was draw diagrams. Well, they're significantly more complex than this, but this is a simple version, okay? You may not think it looks simple, and that's why I will take you through it slowly, okay? So here is what we call a quantum computing circuit, and the first thing to know is that time runs from left to right, okay? The second thing to know is that each of these horizontal lines represents a quantum system. Indeed, it's a two-state quantum system, much as we discussed before. So you can imagine maybe I have an atom represented by each of these lines. And here's some trapped ions just to show you what this might look like. Okay, so what do we have to be able to do a computation with this system? Well, we need to be able to prepare inputs. So there's a case of preparing this atom, and here you see a symbol for how this atom has been prepared. So each of these symbols reads naught, but then there's this funny Greek letter here which tells us that this atom's been prepared in some more unusual state. At the end of our computation, we have to be able to read out outputs. We have to obtain information from the system. That's our answer, if you like. But then we also have to be able to compute. And the remarkable thing that David Deutsch showed was that any unitary transformation on a physical system can be decomposed into sort of what I'm going to tell you in a second is a simple set of tasks acting on two-state quantum systems. And that's another jump in conception. You take any arbitrary quantum system, it might have 100 levels, and now you fit it, if you like, to a set of two-state quantum systems, which are all independent until they're interacted. And then you want to be able to perform a simple set of operations. And this set of operations is relatively simple. There's two types. There's one type where actually you go in and you just tweak one of these quantum bits, these qubits, these quantum systems. And then the other type, which occurs relatively commonly, is where conditional on one of these systems, you change another. Okay? You don't go in and measure, you actually do something where these two interact, and this is what spreads entanglement, these non-local correlations through the system. Okay, so you can see some examples, and one of the big steps forward in this work really was that these interactions don't have to involve all the particles in the computer, they can involve small numbers, so 2 or maybe 3. And this is a big breakthrough, but actually realizing quantum computation is a much harder business. You now have to go to experiments, and experiments in theory are sort of a long way apart in this field. Okay, so here's the experiment. This is the recent experiments we were doing at NIST. And this is an ion trap. So what are you seeing here? You're seeing an alumina wafer. It's patterned with gold. And there's a little slot in the middle. And in the middle, if we apply electric fields to all of these gold electrodes, that is, we apply voltages to all of these guys, then what we find is we can trap individual atoms in that slot in the middle. And they're really well confined. These atoms will sit there all day. Okay? And it's a little more than that. We can actually make these atoms do something now. What can we make them do? Well, we can make them do quantum circuits, okay? And this is really the first multi-bit quantum computer. What this is, there are 2 qubits in this system. There are some of these interactions, so that's these lines that connect the 2 qubits. And then here are some operations that we apply to individual qubits. And why do I call this a programmable quantum computer? Well, this thing can do anything you like to 2 qubits, right? It can do absolutely any quantum operation on these 2 qubits. And how do I program it to do that? I program it by setting what I do in these rotations here. So that you tell me what you want me to do to my quantum system. I then go and program in this A, X, Y, etc. And then my quantum circuit actually does what you asked me to do, okay? And so that's really the first programmable quantum computer, and it's a flexible device, though obviously this is not going to be factorizing large numbers or finding prime factors or anything like that. The biggest number it can even store is number 4, okay? It's not big, okay? But there's more to this experiment than just demonstrating some cutesy sort of demonstration of quantum computing, if you like, or that we can do flexible quantum computing. This experiment actually was incorporating many of the techniques you need in terms of moving towards a large-scale computer. So let me give you the vision. Okay, the vision is drawn up in a paper from Dave Wineland back in 1998 or so. And the vision is that you have a whole set of ion traps, essentially, but they're all interconnected such that you can, by applying different voltages or time-varying voltages to all these electrodes that are drawn here, you can shuttle ions throughout the array. And what does that mean? Why is that important? It's important if you're building a large-scale device, because you might have a qubit over here and a qubit over here, which you would like to interact, okay? So what do you have to do? You have to bring them all over to bring them together, and then you can push them together dependent on their information, and that is the interaction that you want. But if you've got a large device, then they're not naturally sitting near each other. They can't interact strongly at all. You have to be able to bring them together. And so that's what all of these lines are doing. They're transporting. And actually, if you look at many architectures for a quantum computer, most of what they do will be to transport information around. And what these experiments were showing was that in our little system, we could demonstrate one region of this trap array. And in particular, we could demonstrate all the tasks that are needed for going towards this large-scale quantum computer, all the tasks that are required from one of these little regions. And so what did that include? It included controlled interactions. It included operations on the individual quantum bits. It included initializing the system, and it included detection. And crucially, when we do any of these tasks, they don't interfere with our ability to transport information. And when we do transport of information, it doesn't interfere with any of the tasks that we'd like to do here. And I think, to my knowledge, this is probably the only quantum computation system in which you can say that at present. Okay, but nevertheless, it's a pretty long way to go. Okay, so what I described was a very simple quantum computer. And what I meant to describe was something that's horrifically complex, okay? So this is the lab that we had at NIST in Boulder, and somewhere in the back there is the ion trap, and it's something like a couple of millimeters long sitting in a vacuum can. In fact, you can see the vacuum can just there if you look very carefully. Okay, and what's all this stuff doing? This is controlling all the laser pulses. In fact, it's not just doing that. In the foreground, what you see is lasers. They're producing the light that we use to control the ions. And then it goes through a forest of mirrors and lenses and wave plates and diffraction gratings and all sorts. And then eventually it makes it out of the trap, and it's relieved to be a pulse that you actually use on the ion, okay? And what these things do is they allow us to control the set of pulses, and there are many thousands of these pulses that go into actually producing these simple quantum computations. That's not the only complexity battle we have. The other one is that I really just showed you a very basic array with maybe 5 places where we could put ions, okay? And in fact, we used 2, okay? We have a struggle now, or the thing we need to do at the next level is to take this from a small system into being a much more complex system. And so here you're seeing, if you like, the next generation of traps, where instead of having 6 zones, we now have 150 zones, okay? And the way we can do this is by taking advantage of microfabrication techniques and just being able to print a trap onto a surface. And so that's something we're going to pursue here at ETH and take advantage of the very nice facilities of the first lab in order to generate these small-scale traps with complex geometries, and that should enable us to make more complex quantum states and to explore quantum dynamics at a higher level of complexity. Okay, so there is a long way to go. What do we learn as we're going along towards these goals? Are the benefits to societies rather than just this sort of dream in some 20, 40, 80 years in the future of this quantum computer? And I would say yes, there are certainly things we're learning. And in fact, you've already seen the first spin-out of technology from quantum computation, okay? What you're seeing here in this picture is a beryllium ion. And what I've written here is not beryllium ion, I wrote beryllium control ion, because the other thing that you're not seeing in this picture is that sitting next to it is an aluminum ion. Oh man, I said aluminum and I meant to say aluminium because I'm British. Okay. So what's remarkable about this aluminium ion, the remarkable thing about this ion is that when I look at a 2-state system in that aluminium ion, the clock is extremely steady and extremely well defined. Okay? And that's a very remarkable thing. And in fact, very stable clocks are what we use to stabilize our time that we use in the world today. So things like GPS all run off atomic clocks. And the best clock in the world right now, or the best frequency that we can pull out in terms of developing a clock, is this aluminium ion. And the only way we can control it, such as we can get information from it and control it to use it as a clock, is by storing it next to a beryllium ion and taking the information out through the beryllium. And what that uses, it uses the fact that these 2 ions are charged, they repel each other, and these are techniques, the use of this repulsion and the coupling of information through this repulsion is exactly techniques that were developed for quantum information processing. Okay, so the first spin-out really of the quantum information drive in trapped ions certainly is that now we have a clock, if you like, a frequency standard that's a factor of 50 better than cesium, which is currently used to define the time that we run by. What else might we be learning? The other things we're learning about is actually how to characterize quantum systems, right? So by going into the lab and trying to do these things experimentally, we find out about the difficulty of doing that, okay? And so one way in which that manifests itself, I told you about already. You try and make a hell of a lot of measurements, so 656,000 or something, to extract the state of your system. And it's got an extremely large amount of information in, but the thing you should notice is that really there aren't as many pieces of useful information, that's these blue peaks, as there are fully elements in this matrix. And so the stimulus here has been that now people are thinking pretty hard about how to extract useful information from quantum systems rather than all the information from quantum systems. Okay, and that's a big drive, and I think that's something that we're seeing new techniques for measurement and new techniques for characterization, and this is a field that's pushing forward. And then the other thing we're learning about, and I'll tell you more about this in the next couple of slides, is interactions between quantum systems and the environment, and how quantum systems evolve, if you like, when they're coupled to the environment. So let me tell you a bit more about that. So what I should take you back to is the system we thought about before and these non-local correlations and the need to describe the whole system if I want to extract the quantum nature of these correlations. Okay, and so let me just remind you, we saw this nice oscillation, but only when we considered 2 particles at that point together, but I'll use it to represent the coherence in many particles. But a quantum system, it never lives on its own in the world. There are always, it sits in an outside world, and that outside world also has particles. And unfortunately, more time than we would like, these outside particles come along and they bump into the quantum system, and maybe they go away again pretty rapidly. But in some of these cases, they become entangled. That is, they develop correlations with the quantum system. And now look what I'm doing. I'm trying to read out about quantum mechanics, but I'm not treating the whole system that's involved. This particle has now become involved. It's got a shared clock, if you like, with this inner particle. And so what do I get if that happens? I get nothing. Okay, I get flat lines. And so that's a problem, because essentially going from a situation where I had something working nice and quantum mechanically, I go to something where it really looks like classical physics. And this is a big problem for a quantum computer, because if you have 1,000 qubits, the chances are one of these guys will come in and steal some information, and then you end up with basically a classical computer again. So quantum computers will also spend a vast amount of their time trying to reject noise. Unfortunately, my former supervisor, Andrew Steen, and others came up with techniques for quantum computers to be able to do this. But what I'm going to tell you about today is not just these sort of simple models where the environment instantly destroys all coherence. There's a little more complexity to the environment than that. Okay? And that's partly because environments in themselves are complicated systems, and specifically when you've got quantum devices that are sitting inside a solid, they're very strongly coupled to this environment, and the couplings sometimes are faster than the couplings within, say, within the quantum system. They're also sometimes faster than couplings within the environment. And what does this lead to? Well, one effect that this leads to is memory. So here, this particle may come in, it may interact with my quantum system and run away again, but in some cases, that information may return to the quantum system. And so if I start to have memory, and in particular, if I start to have situations in which, while it's away, the system, the environment interacts with other parts of the environment, and then this information partly comes back, I have the sort of start of a very complicated situation, because I start to have to model this environment. Okay, and so here, again, complexity comes into the system, and I have to sort of start working with many-body systems, and this becomes a challenge. But another more recent sort of realization from working with systems coupled to their environment, if you like, and this really goes hand in hand with quantum computing, that you study how to isolate your system from noise, and in so doing, you learn stuff about the interaction between systems and their environments. Okay, and so one nice thing that was realized recently is that the environment can actually work in your favor in some way. So let's consider a situation here where these are really my quantum system, but by some prior interaction, they ended up entangled with something in the environment. And then something else happens in the environment, another particle comes in and interacts with this guy. Well, what can happen in that system is it ends up by decoupling the environment but leaving these two entangled. Okay, so it generates these quantum correlations that we kind of like to have in our system, we'd like to produce, and leaves it sort of dark to the environmental system, or decoupled from the environment. And that's something very interesting. It sort of gives us quite a number of ideas, all the way to maybe implementing quantum computation exactly in this sort of fashion, towards driving the system into interesting quantum states by coupling it to engineered environments, environments which are dominated by dynamics that we put into the system. And so that's the other part of what I'd like to do at ETH, and this is where the group is going, is towards realizing these sort of models, these manipulations of the environment to create quantum states. And if you want to do that and you want to examine these effects in a very controlled setting first, well, you better start with something that naturally is quite robust against interactions with this environment, and that's why we start with beryllium ions, which are extremely robust against interactions with their environment. So a quantum state in a beryllium ion, and I should have pulled up the data for this, can live for about 15 seconds, okay? And that's a very long time for quantum states. Okay, so what are we going to do? We start with a quantum system that's made up of beryllium ions, and we add to it a different type of ion, one that we can address completely independently by shining on a different color of laser, and we use that as our environment. Okay, so now here we've got a sort of bi system, if you like. One part of the system is the beryllium ions, the other part is the calcium. And here is now a new sort of system for taking on quantum state engineering and taking on studies of systems coupled to their environment. But in this sense, we're doing a simulation of that system, because we have absolutely full control over not only the evolution of the environment, the evolution of the system, but the coupling between the two. Okay? And so with that, I'd like to thank you. This promises for me an exciting time in terms of realizing new types of control and for quantum systems and novel quantum states. And with that, I'd like to thank you for your attention. And I hope I've pointed out to you that we sort of are making some progress towards maybe meeting this demand of contacting quantum mechanics to bulk systems. And we may in the future provide nice insights into the intricacies of the decay of the quantum system into a classical system. Thank you very much.